Okay, in this section of the chapter, we're going to start to talk about solutions, how we calculate solutions, how we talk about solutions. We really want to get familiar with the terminology here because being able to calculate with solutions is such a big part of chemistry, especially your lab work. Here are some terms that you need to know. Okay, we went over some of this earlier. For example, we call homogeneous mixtures solutions. So when we're talking about solutions concentration and solution stoichiometry, we're talking about homogeneous mixtures. So we're going to be mixing two different things together. We have two components of the solution that we have to differentiate. The first is the solute, that is the part of the solution that changes state. It's also the part of the solution that is the minor component. Okay, so whatever exists in a smaller quantity, that's our solute. The solvent is the other stuff, okay? So the solvent is going to be the major part of the solution. It's also going to be the part of the solution that keeps the same state throughout. So if it starts as a liquid, it's going to end as a liquid. If you look at the example up top, when table salt is mixed with water, it seems to disappear, become liquid. Okay, so now we have two components here. We have a salt component and a water component. The salt dissolves, it changes state, and it becomes a liquid. All right, so in our mixture that we're describing up here, the salt would be the solute and the water would be the solvent. Okay, now when you have a situation where both of your components start and end in the same state, the only way that you're going to be able to tell which is the solute and which is the solvent is by quantity. All right, so I have two examples here. If a solution has 10 milliliters of ethanol and it has 90 milliliters of water, okay, 10 ethanol, 90 water. In this case, ethanol would be the solute because it exists in the smaller quantity. Water is the solvent. On the other hand, if I have a different solution, and this solution has 10 milliliters of water and 90 milliliters of ethanol, in this case, water is the solute and ethanol is the solvent because water is the minor component in this case. Okay? We know that mixtures do not have a set proportion or a set amount, so the composition can vary from one sample of the mixture to another sample of it. All right, something again like salt water, we've talked about how you might have a different concentration of salt in the water depending on where you get your sample from. So to describe that level of solute that's dissolved in the solvent, we are going to need, particular terminology to talk about that, right? We have what are called dilute solutions, and we have concentrated solutions. Dilute solutions are going to have a very small amount of solute when you compare it to the amount of solvent that's present, whereas concentrated solutions are going to have a large amount of solute compared to the solvent that's present. And if you want to think about making yourself like iced tea or something like that, again, and that's the best way to differentiate between dilute solutions and concentrated ones. Numerically, we are going to talk about concentration in terms of molarity. Okay, molarity is our big concentration term in chemistry. The term molarity means the amount of solute in moles divided by the volume of a solution in liters. Okay, so it's moles divided by liters. That's what molarity means. Molarity is represented by a big M, okay? And it's going to be used to represent the concentration of a solution. So I wrote out, it's sort of a repetitive example, but I wanted you to see the different ways that you can represent the same idea. So let's imagine I have some glucose dissolved in water, and the solution is 0.15 molar. all right? That would be represented in shorthand like this, where you have 0.15 and then a big M. What that means is that I have 0.15 moles of glucose over liters of solution. Or more specifically, I have 0.15 moles of glucose for every 1 liter of solution. Okay, so this is the most defined version of our molarity unit. When you see something like 0.15 molar, it means that for every 1 liter of solution, you have 0.15 moles of that particular solute. So let's look at an example. Okay. How many moles of solute are required to make 3 liters of a 2 molar solution? Okay, so to solve this out, we're going to set up our molarity expression. Okay, so that's a really bad 2. Fix that. We have a 2 molar solution. And we know that molarity means moles of solute over liters of solution. And we know that we have 3 liters of solution here. Okay, so we can actually solve this out for moles. So moles of solute equals 2.0 moles per liter, which is the definition of molarity, times 3.0 liters. And you'll notice here that our liters cancels out, and we're left with a unit that's just moles. So 6 moles of solute are required. This problem leads us into something that you're going to see quite often, and you'll hear me say it quite often. This particular relationship between molarity and volume. Okay, you're going to be given molarity values and volume values pretty frequently when you're doing your chemistry calculations. If you have a molarity and you have a volume that's in liters, I'm going to put an L down there so it represents the volume that's in liters in particular. If you multiply those two values, you end up with moles. Molarity times volume equals moles. So whenever you're given a molarity value and a volume value, you're being given a mole value, even if that's not being explicitly stated in the problem. Okay. So we see here that we have an answer of 6 moles of solute required to make this solution. Let's look at some more practical applications of this. So if you dissolve 25.5 grams of potassium bromide in enough water to make 1.75 liters of solution, what is the molarity of the solution? And they were nice enough to give us the molar mass of potassium bromide here. So you have to ask yourself, what do I need to know to answer this question, right? The definition of molarity is moles divided by liters of solution. You are given 2 pieces of information here. You're given the grams of KBr, and you are given the volume of the solution, all right? So this volume value is good. We can use that in our molarity calculation. However, this value right here, this 25.5 grams, in this form, it's pretty useless to us, okay? We're not looking for a grams divided by liters calculation. We need a moles divided by liters calculation. So what we want to do is we want to take this gram value, we want to convert 25.5 grams of KBr into moles of KBr. And once we have a mole value of it, then we can calculate a molarity. So pause your video for a second and try out this calculation on your own. And now we can talk through it. So we're going to take the 25.5 grams of KBr, and then we're going to use the molar mass of KBr that we would get it from the periodic table if it was not given in the problem. And then we can calculate the mole value for KBr here. Once we have the moles of KBr that are present, now we can set up a molarity calculation. So molarity is going to be moles of KBr divided by liters of solution, okay? And that is 0.122 molar KBr. So here's the next one. Again, I would like you to try this out on your own. Okay, so we're going to go through the same process as before. We have 45.4 grams of sodium nitrate, and we're going to need to create a total volume of 2.50 liters of solution. So to figure out the molarity of that solution, we're going to need to know the moles of sodium nitrate, and then we're going to have to divide it by the liters of solution that are present. So we'll take our gram value of sodium nitrate. We'll use the molar mass here to calculate the moles of sodium nitrate. Once we have the moles of sodium nitrate, we can divide it by the liters of the solution that we're looking for, and that will give us the molarity of the sodium nitrate. Now we're going to look at another. I think we have 2 more examples of this. This one I think I'm gonna have to do on my whiteboard though. Okay. So now we're going to look for the mass of the KBr in grams that we need to make 250 milliliters of a 1.5 molar KBr solution. Now, the reformatting of this might seem stressful initially, but just think about the definition of molarity whenever you're looking at one of these problems. This is going to be your main source of information here. Molarity is moles divided by liters. Okay, so whatever information you're given in your problem, you're going to look at how you can relate it back to this expression. So over here, we already have a molarity value. That's great. So we know that we have one piece of information here. And we almost have another piece of information because we have the volume value, but it's in milliliters. So if we reorient our formula here, we again can see that molarity times volume will give us the moles of KBr we would need to make up our solution. Okay, make a little arrow. So our molarity is 1.50 moles over liters. We'll multiply that by the volume in liters, which will be 0.250. Right, our liters will cancel out. Let's get our calculators. 1.5 times 0.2500. So our mole value for KBr, which is our solute, is 0.375 moles. Okay. Now we want to know how many grams of KBr we were going to need to add to the solution. So to figure out the gram value from this, we will take the molar mass. We know that for every 1 mole of KBr, there are 119 grams. Which means that we would have to add 44.6 grams of KBr to 250 milliliters of water to make a 1.5 molar solution of KBr. Okay, so hopefully it's clear to you that this is basically what we're doing here. We're using our molarity unit as a sort of conversion factor. And we can move between the moles of the solute in the liters of solution using that conversion factor. Okay, so if we know one of them plus the molarity, we can find the other one. Just as a quick concept check, checking in the law of conservation of mass, pretty much. If we dissolve 25 grams of salt in 251 grams of water, what is the mass of the resulting solution? Okay, hopefully that's clear. So let's look at a few different versions of this problem now. How many liters of a 0.125 molar sodium hydroxide solution contain 0.255 moles of sodium hydroxide? So this is very similar to what we did before, except here we are going to be looking for the liter value or the volume value instead of the mole value. Okay, so let's look at how to solve this problem. Now again, we're going to start with our molarity expression. So molarity equals moles of our solute, which in this case our solute is NaOH, divided by liters of solution. All right. And now we're told that we have a 0.125 molar NaOH solution. So that's our molarity value. And we are told that it contains 0.255 moles of NaOH. All right. So now we have to rework this equation so that we can solve it for liters of solution instead of moles, which we've been doing lately. Okay, so I'm going to multiply both sides of the solution by liters. So times L times L. And I get liters times molarity equals moles of NaOH. Okay, now I'm going to isolate the liters by dividing by molarity, both sides. So I get a final expression that is, let me erase the top. I have a little more room. We'll erase this first one. So my formula that I'm going to work with here is liters is going to equal moles of NaOH divided by molarity. Okay, but hopefully that you followed the step-by-step process there, where we just shifted around that initial equation until we got this new one. And we're shifting it so that everything that we have a known value for is on one side and everything that's unknown is on the other side. Okay, so now we can plug in the values that we know from the problem. We know that the moles of NaOH are 0.255. And we know that the molarity is 0.125. So when we divide those two values out, we'll get the liters of the solution. So we have 2.04. So that's our volume of solution. Okay. All right, let's look at another example here. What volume in milliliters of 0.175 molar methanol solution contains 1.9 times 10 to the negative 2 moles of methanol? All right, so we're going to attack this problem in a similar way. So pause for a second, try on your own. Hopefully you've done that. You're not just watching me do stuff and then hoping you remember how to do it on your test. Okay, so our first step here is that we're going to write out our molarity expression. Here's our shorthand version of it, moles over liters. And in this case, we want to know a volume value, right? So we're going to algebraically solve the expression for liters like we did last time. Or actually, you know what? We'll do it a little different this time. So last time we solved it algebraically. This time, let's just plug in values and solve. Okay, so we have a 0.175 molar solution, and that equals 1.9 times 10 to the negative 2 moles divided by x liters, right? So now we're going to multiply both sides by the x liters. So when we multiply both sides by the x liters, obviously it goes away on the right side and it transfers to the left side. So we end up with 0.175 molar solution times x liters equals 1.9 times 10 to the negative 2 moles. Okay, now we'll divide this by 0.175 molar. And our liters value is going to be, small drum roll, 1.9 times 10 to the negative 2 divided by 0.175 is 0.109 liters. Our question asks us to give this value in terms of milliliters, so I will very quickly do a metric conversion. All right, and this is 109 milliliters. Okay. Okay, here's our next example. In this case, we're making it a little bit more complicated. We want to know how many grams of sucrose, which is C12H22O11, are in 1.55 liters of the 0.758 molar sucrose solution. Okay, so they're giving us a molarity and a volume here and asking us for a gram value. So that's just one step further than what we've been doing before. Okay, so take a minute and try to write out your roadmap for solving the problem. Okay, take the time to do this. It's a really important skill to be able to do this on your own while you're taking an exam. Okay, so hopefully you've started that out on your own. Per usual, we're going to start out by writing out our molarity relationship. Molarity equals moles over liters. Okay, in this case, we have a molarity volume and a volume value. So we can rework this as molarity times liters equals moles, or molarity times volume equals moles, but our volume is in liters. Then we can plug in the values that we know. So we have a 0.758 molar solution. We'll multiply that by our volume, and that is going to give us our mole value of sucrose. So 0.758 times 1.55 equals 1.1749 moles. Okay. Now that we have a mole value specifically for the sucrose, right? Because this expression here, it's moles of solute divided by liters of solution. And our solute in this case is the sucrose that's dissolving in the water. So now we're going to find how many grams of sucrose we have in the solution. So we'll take our mole value for sucrose, and now we're going to multiply it by the molar mass of sucrose that was so nicely given in the beginning of the problem. Okay, and that is 402 grams of sucrose. All right, I think we have one more to try. Okay, so here is our last question. How many milliliters of the 0.155 molar potassium chloride solution contain 2.55 grams of potassium chloride? So in this case, we're given a molarity and we're given a mass, okay? So hopefully at this point, whenever you see a mass value, you automatically are thinking to yourself, how can I turn that gram value into a mole value? Once you have a mole value and a molarity, then you'll be able to figure out the volume of solution that you'll need for this particular mixture. Right, so again, pause here, try to make up a roadmap for yourself, and then I'll do it out on the whiteboard. All right, so a good starting point here would be to get rid of this gram value. We very rarely are going to need those in these calculations. So we have 2.55 grams of KCl. Our molar mass KCl is 74.55 grams per 1 mole. So let's figure out our mole value first. Okay, now that that's done, now we can look at our molarity expression. All right, and we are going to solve it for liters. Okay, so if you do the algebra out, now we've done it longhand twice, so I'm going to start to shorten it a little bit in our whiteboard calculations. So to find liters, we're going to take the moles and divide it by the molarity. And if you remember that moles is equal to moles divided by liters, it's, you can watch the units cancel each other out and you'll end up with the correct unit of liters at the end. So now if we do our division, we end up with a volume of 0.221 liters. And we are asked to report this in terms of milliliters. That's 221 milliliters. Okay. Okay, so let's move on to the next section here, where we're going to start talking about how to dilute solutions so that we can work with them in real lab experiences. Okay, when you hear the term stock solution, we're talking about how the chemicals are coming to us straight out of the manufacturer. Okay, they are our most concentrated solutions. We store our stock solutions separately from everything else to make sure that they're not contaminated. And from those stock solutions, we create more dilute solutions, which are of lower concentration, that we can practically use in lab work. Okay, not every experiment calls for concentrated solutions of material. Very few of them do. So we are often diluting stock solutions to make them appropriate for what we need to do in lab. Okay, now to do this, we are going to basically change the volume of the solvent that our solution um, has. Okay, I don't know, that doesn't make it very clear initially, but I'm gonna hopefully show you something that clarifies it. When you have a stock solution, okay, and you're going to dilute it. Say that you have an aqueous solution of hydrochloric acid, okay, and it's a very concentrated solution, like 12 molar or something like that. So you have 12 moles of hydrochloric acid for every 1 liter of water. Now, if I want to dilute this solution, I'm going to add more solvent to it, okay? So I'm going to need to increase the volume of the water that's present, okay? Now, when I increase the volume of the water that's present, that increases the volume of the overall solution. But what it does not do is change the moles of the HCl that are present. So the amount of my solute is not changing here, just the volume of my solution. So if we look here at this example, we have solution A, I guess we can call that, and that is the solution that's before dilution. So this is our stock solution here. And if each of these little red spots represents a mole of solute, then in my stock solution, I have 6 moles of solute. All right. Now I'm going to add solvent to this. Okay. So what do I add over here? Maybe like twice as much solvent. So the volume of my diluted solution is much larger than the volume of my stock solution. But the moles of my solute that are present, still 6. Okay, so the moles of the solute, that doesn't change, just the volume of the overall solution. And because molarity is a ratio of moles divided by volume, that means that our molarity will change when we change our volume value. Okay, we get an expression from this, or a relationship that allows us to kind of calculate different aspects of our solution depending on the information that we know. So if we have the molarity of a concentrated solution and the volume of a concentrated solution, and we multiplied those things out, that would be the same as if we had the molarity of the dilute solution and we multiplied it by the volume of the dilute solution. I'm going to switch to my whiteboard here real quick just to kind of give you an idea of why. We already said that molarity times volume equals moles, okay? And we also have just said that the moles of our concentrated solution are going to equal the moles of the solute, specifically of our dilute solution. Okay, so because this relationship is true, because our mole value for the dilute solution and the concentrated solution is the same number of moles and only the volume is changing, then if we take the molarity times the volume of the concentrated solution, we can equal that to the molarity times the volume of the dilute solution. So then if I know 3 of these values, I can always find the 4th one. All right, hopefully that makes sense. Oh, gave that away. This is just a concept check. Okay. Consider the following reaction. Um, what is the limiting reactant if you mixed equal volumes of 1 molar solution of A and 1 molar solution of B? Just a recall back to our limiting reactant stuff. Now we're looking at it in terms of concentration. So you can imagine that if you have a 2-to-1 ratio here, that you're going to be using up your A twice as fast as the B. So if you have the same molarity of each and you have equal volumes of each, that means that you're going to be running out of A before B. Now let's look at some of these solution dilution questions. Okay, so to what volume should you dilute 0.200 liters of a 15 molar NaOH solution to obtain a 3 molar solution of NaOH? Okay, now the biggest and most important step here is going to be to organize your information, all right, before you try to solve this problem. So we're going to bring this up to the whiteboard so that we can look at it. Okay, so let's look at how we're going to organize this information. The standard way that you see this equation, this dilution equation, is M1V1 equals M2V2. Another way that you can write it, and the way that I kind of like to write it better because I feel like it helps me sort out my information, is the molarity of the concentrated solution times the volume of the concentrated solution equals the molarity of the dilute solution times the volume of the dilute solution. Okay, I feel like it might be easier to see how those things go together if we sort it out like that. And you have to pair them correctly. You can't just throw the different molarities and volumes together however you'd like. You have to make sure that you pair up the concentrated information, you pair up the dilute information. So the statement, to what volume should you dilute 0.200 liters of a 15 molar NaOH solution to obtain a 3 molar NaOH solution? All right, so that first bit of information we got, the 0.200 liters and the 15 molar, that is both describing our concentrated solution or our stock solution. So over here, we have our two pieces of concentrated information. Okay, now the molarity that we are trying to get to is 3 molar. All right, so we're starting at 15 molar and we want to dilute it to a 3 molar solution. And we don't know what this volume is. That's our unknown. So now we're going to divide this by 3 molar. Divide this side by 3 molar. Okay, our molarities are going to cancel out. And then we can do our, we don't really need to do calculator work for this. So we can, and we end up with 1.00 liters is our volume for our diluted solution. Okay, let's try another one. Okay, so here's another example. Why don't you guys pause and try to do this one on your own before we do it together. Okay, so we're going to start our setup the same way. Molarity of the concentrated times the volume of the concentrated, molarity of the dilute times the volume of the dilute. So in this case, we have 100 milliliters of a 5 molar calcium chloride solution, and we are trying to get to a diluted 0.750 molar calcium chloride solution. So we have 5 molar times 100 milliliters equals 0.750 molar times our diluted volume. Now you're going to notice that when we have these dilution equations, that we don't necessarily have to convert all of our volume values into liters like we were doing for our molarity calculations. And this is because of how this equation is set up, okay? As long as our volume values are the same unit, we can use whatever volume values we would like, right? But they do have to be matching volume units. So in this case, I'm going to divide both sides by 0.750 molar. My molarity cancels out, and when I do this calculation, I'm going to be left with a volume that is in milliliters. 5 times 100 milliliters divided by 0.75. So this is my diluted volume. Okay, here's another example. We're going to make it a little bit different here. What volume in milliliters of a 6 molar sodium nitrate solution should you use to make 0.525 liters of a 1.2 molar sodium nitrate solution? Okay, so we're starting with a 6 molar solution and we're going to dilute it to 1.20 milliliters. We want to make 0.525 liters of the diluted solution. So those values are going to go together. And we want our final volume in milliliters, okay? To get our final volume in milliliters, you can either convert the 0.525 liters into milliliters before you start the calculation, or you can change your final result into milliliters. Either option is perfectly acceptable. So let's set up our equation. Okay, in this case, we have the molarity of the concentrated solution. And we have the molarity of the dilute solution. And we have the volume of the dilute solution. I'm going to write the 0.525 liters as 525 milliliters because we want our final answer in terms of milliliters, okay? Once we have all of our information written out and sorted properly, now we're going to solve for the unknown variable. Okay, so this goes away and this unit goes away. Now let's do some calculator stuff. 1.20 times 525 divided by 6.00. And we get a volume of 105 milliliters. Okay. What this means, okay, now in terms of like lab work, if this is the volume of our concentrated solution that we need, that means that we should take 105 milliliters of a 6 molar solution of sodium nitrate, and we should dilute it to exactly 0.525 liters. And at that point, our solution will have a molarity of 1.2 molar. All right, let's try one more example of this dilution equation. In this case, we want to know what the molarity of the glucose stock solution is if 22 milliliters of it were then diluted to 11 liters and a 0.0010 molar solution was created. Okay, take a minute, pause this, sort out your information the way that you think it should go. Okay, and then we'll continue on the whiteboard. Okay, so we're going to start by organizing. Right, so in this case, for the first time, my molarity of the concentrated solution is my unknown here. I know everything else, okay? So I'm gonna plug in what I know, MC, my concentrated volume is 22 milliliters. Okay, I'm gonna change that into liters so that my two volume units match. Okay, so I changed my 22 milliliters into 0.022 liters. Now my diluted molarity is 0.0010, and my diluted volume is 11 liters. Okay, now I'm going to solve. And the concentrated solution that I started with is 0.0010 times 11 divided by 0.022. It's 0.5 molar. Okay, so that's all of the types of dilution questions that you would see. You really are not going to have to worry about using this equation except for when you read the word dilution in a problem. All right, it's pretty specific to that. The last topic that we're going to cover in this recording is what's called solution stoichiometry. Okay, we've looked at excuse me, we've looked at stoichiometry in regular reactions where we take a balanced equation and we relate the moles of thing A to the moles of thing B. Okay, we could do the same thing with solutions. This is because if we have the molarity of a solution and the volume of a solution, that is the same thing as having the number of moles of solute in that solution. Okay, and once we know the moles of a solute, then we can relate it to anything else that's in a solution. So if we know the molarity and the volume of one component, we can figure out what the mole value of that component is. Once we know the moles of that, we can use the balanced chemical equation to convert it to the moles of a different reactant or a different product. Once we have the mole value of that product, then we can use it to find whatever we're looking for. If we're looking for the volume of that thing, we can find the volume of it. If we're looking for a gram value for that thing, we can find the grams of it. Okay? But we're going to be using both relationships. We're using molarity times volume equals moles, and we're using our balanced chemical equation to relate the moles of one thing to the moles of another thing. All right, so let's look at this example. What volume in liters of a 0.150 molar KCl solution will completely react with 0.150 liters of a 0.175 molar lead nitrate solution, according to the following balanced chemical equation? So we see here that 2 moles of KCl reacts with 1 mole of lead nitrate to form 1 mole of lead chloride and 2 moles of potassium nitrate. All right, so that will be important because we need to use the information from our lead nitrate to find information out about our potassium chloride. Okay, and look at the information that they give us for the lead nitrate. They give us a volume value and they give us a molarity. Molarity times volume is moles. So right away, we know what the moles of lead nitrate is going to be. We can just multiply these two values. Once we know the moles of the lead nitrate, then we can use our balanced chemical equation and relate every 1 lead nitrate to 2 moles of KCl. once we have a mole value for KCl and we have the molarity of KCl, we can then find the volume of KCl. Okay? Take a minute, see if you can set up something, set up your roadmap to figure this out. And then I'm going to put up the slide with the actual solution. But take a minute and try it, okay? Now you can do this in multiple steps, or you can do this in one step like I have it written here. So I started out with the volume of the lead nitrate, and I'm multiplying it by the molarity of the lead nitrate, okay? And we see that the liters when I do the molarity times the volume, or in this case, the volume times the molarity, my liters unit cancels out, and I'm left with a unit of moles of lead nitrate. That leads me to my second conversion, and this conversion comes from the balanced chemical equation. I'm going from moles of lead nitrate to moles of KCl, and these numbers are coming from the balanced equation. 1 mole of lead nitrate it equates to 2 moles of KCl. Okay, so 1 mole of lead nitrate for every 2 moles of KCl. Now, I want to find the volume of KCl. So I can use the molarity of KCl, which is 0.150 molar. And I can remember back to that first slide discussing molarity, where if I view molarity as a compound unit, moles per liters, then I can manipulate it like I do with a molar mass, right? When I want to find out the moles of something, then the grams of my molar mass goes on the bottom and my moles goes on top. For molarity, if I want to find out the volume of something, my moles is going to go on the bottom so that I can cancel out with the thing that came before, and my volume will go on top. Okay, and it turns out that 0.35 liters of KCl will completely react with the lead nitrate. But some people do not like to do it in one step, so I do want to write it out on the whiteboard in multiple steps. Okay, and then you can decide which way works better for you. Okay, so here's a shorthand version of what we're looking at. So if you want to break this up into steps, we can do that as well. Okay, so the first thing that I'm going to do is I'm going to look at that information that I was given about the lead nitrate. Okay, and I'm going to remember that molarity times volume equals moles. So I can take my 0.175 molar lead nitrate, multiply it by the volume, and I can calculate a mole value from that. Okay, now once I have this mole value, now in my next step, I'm going to use my balanced chemical equation to convert from moles of lead nitrate to moles of KCl. So every 1 mole of lead nitrate needs 2 moles of KCl. Okay, now for my last step, I'm going to use this value here, and I go back to my molarity definition. So in this case, I have a molarity of KCl, and now I have a mole value. So I know I can get liters by taking my moles and multiplying it by my molarity. Okay, so my liters of KCl. Oh, can't see that. Sorry, guys. Got all out of. That's what happens when you rush. Right? I mean, we did this like 5 times before. To find the liters, I'm going to take the moles and divide it by the molarity, obviously. So that's 0.0525 moles over 0.150 moles per liter. And that gives us a volume of 0.35 liters. Okay. So that's the other way to solve it. I'm going to use the first method that I showed you all in one step because that is how I'm used to doing it. But this is a perfectly valid method of breaking it down for yourself if you don't like that other method yet. Okay. Okay, let's look at another question. What volume in milliliters of 0.150 molar HNO3, which you know is nitric acid, solution will completely react with 35.7 milliliters of a 0.108 molar sodium carbonate solution according to the following balanced chemical equation? What mass in grams of carbon dioxide forms? So this is a two-part question. We cannot answer both of these questions in one step. We're going to have to take them one at a time. So we can start by figuring out what volume of nitric acid completely reacts with the sodium carbonate mole values that are given to us. Okay, we'll start there. And we're going to set this up the same way that we did before. Okay, we are given a particular volume of the sodium carbonate. If we take that volume and we multiply it by the molarity, it's going to give us the moles of sodium carbonate. Now notice here in this first step, I've already converted this into liters, right? 35.7 milliliters became 0.0357 liters. And that's because your molarity units are moles per liter. So I want to make sure that when I multiply it by molarity in this step, that my liters will cancel out and I'll be left just with moles of Na2CO3. So once I take my volume and I multiply it by the molarity, I'll be left with moles of Na2CO3. Then I can use my balanced chemical equation and I can relate 1 mole of Na2CO3 to 2 moles of HNO3, right, from the coefficients up here. Once I've converted this to moles of HNO3, then I can use the molarity of the HNO3 to kind of relate back that the 0.150 moles of HNO3 is equivalent to 1 liter of HNO3. So again, we've kind of swapped that conversion factor here. And we know to swap it, and we know to put moles of HNO3 on the bottom because moles of HNO3 was on the top of our conversion up here. Okay, so once we do that and we multiply it out, we get 0.0514 liters of HNO3, which then we can turn into milliliters by multiplying it by 1,000. Okay, now that second question asks about the mass in grams of carbon dioxide that forms. Okay, so we're going to start with the same 2 pieces of information here, but instead of relating the sodium carbonate to the nitric acid, we're going to relate the sodium carbonate to the carbon dioxide instead. Okay, let's take a look at this. So we start here with 0.0357 liters of the sodium carbonate, and then we use the molarity to figure out what the moles of the sodium carbonate would be. So volume times molarity is going to leave us with moles because our liters units, this will cancel out. All right. Once I've calculated the moles of Na2CO3, then I can use my balanced equation to look at the ratio of moles of Na2CO3 to moles of CO2. It's a 1-to-1 ratio here. Once I know the moles of CO2, then I can use the molar mass. 1 mole of CO2 is equivalent to 44.01 grams of CO2, and I can calculate the grams of carbon dioxide that would be produced. Okay, so you can use your molarity and your volume to find a volume value of one of the pieces of the solution. You can use it to find a mass value of one of the products. Okay, we have one more question here, and we'll try this one together on the whiteboard because I don't have it written out. So consider the following reaction. What volume of 0.185 molar Na3PO4 solution is necessary to completely react with 62.3 milliliters of 0.200 molar copper chloride? Okay, so take a minute, please. Try to set this up. Try to do it yourself. Okay, whichever way you feel better about, and then we'll do it together. Okay, so here is the bare bones of this, this question. So we want to know how many milliliters of our sodium phosphate will react with 62.3 milliliters of our copper chloride. All right, so step one, we're going to use this information here because we were given the molarity and the volume here, and we're going to figure out the moles of the copper chloride. Okay, so that'll be step one. So we'll take the molarity, 0.200 molar. We'll multiply it by the volume in liters. Okay, so we can actually say that this is 0.0623 liters. And that's going to give us the moles of the copper chloride. In case you can't tell, I thought I would go back to that other method of solving it for this last problem, just in case that's sitting with you better. I would love to hear feedback about this so I know what works for you guys. So we have 0.01246 moles of copper chloride. Okay, once we know the mole value for this, now we're going to use our balanced chemical equation to figure out the moles of the sodium phosphate that we have. So we're going to start with 0.01246 moles of CuCl2 for every 3 moles of CuCl2. There are 2 moles of Na3PO4. So I have to take my moles, multiply it by 2, divide it by 3, and I get 0.008307 moles of Na3PO4. Okay, so step 3, molarity equals moles over liters, or liters equals moles over molarity. So the moles of my Na3PO4 is 0.008307. I'm going to divide that by the 0.185 molar that I was given initially. And we'll put the liter value down here. So we get 0.0449 liters, and I think I might have asked for the milliliters. So in 1 liter, there are 1,000 milliliters, and that is going to be 44.9 milliliters. So we would need 44.9 milliliters of 0.185 molar sodium phosphate to completely react with 62.3 milliliters of 0.2 molar copper chloride. Okay? So that's it for solution stoichiometry.